So today we're going to review exponents and logarithms, including exponential word problems. You might remember we started with all the rules of exponents, which I put up here. There are the 4 basic rules of exponents. Now you don't have to copy this stuff down. We're going to have a handout that will review all these different rules for you. But this is where the chapter started. Afterwards, we actually introduced 2 other rules that some of you have seen before, but others had not. X to a negative power is the same as 1 over x to that positive power. And the other rule was x to a fractional exponent was the same as the nth root of x. Those were 2 new rules of exponents that some of you had seen and some of you had not. And lastly, there's another rule that says that if x to one power equals x to another power, that can happen only if those 2 powers are the same number. For example, if I say x cubed equals x to the what power, it's pretty obvious that that exponent has to be the number 3. After that quick review of exponents, we then walked and started doing exponential graphs. For example, we started to look at what does 2 to the x look like as a function. And we did this by plotting points because we now know how to deal with negative powers or fractional powers of the number 2. And by plotting points, we found that 2 to the 0 is 1, 2 to the 1 is going to be 2, 2 squared is 4, and we can now do 2 to the negative 1, and that was 1/2, or 2 to the negative 2 was 1 over 2 squared, 1/4. We can even do 2 to the 1/2 power, which is the square root of 2, and by connecting these points, we realize this is the graph of an exponential function. We then tried to analyze what's the domain, what's the range, and the domain of this exponential function happens to be that all x numbers, all real values, work. What's the range of this function? If you look at it, you realize that the y values all have to be greater than 0. That's true for 2 to the x, but what about 4 to the x, 5 to the x, 7 to the x? And we realized pretty quickly that y equals b to the x basically has this very similar shape to that, going through this anchor point 0, 1, having an asymptote at the x-axis, and basically rising very quickly. What about the number 1/2 to the x? What about that graph? Plugging 1/2 to the 0, 1/2 to the 1, 1/2 squared, that would be 1/4. Quickly realize that this is the graph of something like y equals b to the x when b is a number that's less than 1. These soon became exponential growth, or what they call exponential decay. But the graph of an exponential function basically has these properties. The domain is all numbers. The range are numbers that are larger than 0. They all go through this one anchor point, the point 0, 1, and they either increase very rapidly if b is larger than 1, or they decrease very rapidly if b is a fractional value less than 1. With that all set, we then could deal with problems like y equals 2 to the x minus 1 plus 5. And we could expect that you could take the basic parent function and remember, how does that shift or alter the graph? How does this shift or change or alter the graph? And remembering your transformations, we realize that this will raise it by 5. And of course, what this does is shift everything over 1. The only key point that we sort of remembered of the parent function was this one. That point used to live at 0, 1, Now it moves over 1 unit, so it's over here, and it moved up 5 units, so now it's living up here at 1,6. We moved it over 1, we moved it up 5. All the points in the graph will move over 1 and up 5. In particular, it used to have an asymptote at the x-axis. That asymptote will now be moved up 5 and live at y = 5. And so this graph now looks like this. So we could expect you to take the basics of a new graph and a new behavior, a new class of functions, and now that you know what the basic look of those graphs, we can now shift them and alter them in different ways. Right. Those are exponential graphs. What about exponential equations? Well, we started with equations that look like this. An equation of the type 4 to the x minus 1 equals √8. Now, at first glance, that looks like a very complicated equation, but we're going to lean on this fact, this property of exponents. What's going on here is that you have a common base, and the common base is the base 2. I could rewrite both sides as 2 to a power, and this is 2 to a different power. So, for example, this could be thought of as 2 squared to the x minus 1. Using property number 3, I could rewrite that expression as 2 to the, I'll multiply these exponents, 2x minus 2. Square roots, I now know, because that's a square root, that's the same as 8 to the 1/2 power. But 8 can be thought of as 2 cubed. So 2 cubed, furthermore to the 1/2 power, that's going to be 2 to the 3/2. Once I get it to this stage, 2 to this power equals 2 to that power, I can then apply this fact. The only way that these can be equal is if their exponents are the same. So now I know that this exponent has to be the same as that exponent. I can then solve for x by using my basic algebra skills. I could add 2 to both sides. Going for common denominator, that's the same as 4/2. So I get 7/2. And then I have 2x equals 7/2. I can get x itself would be 7/4. That's the power that satisfies the original statement. These type of problems are called exponential equations that have a common base. If I change this problem so it's not 4 to the x equals √8, but if I said 4 to the x equals a number like 7, then I can't use this process because 7 does not share a base with 4. You cannot think of them as the same number raised to a power. So the question then comes, well, how do I solve our exponential equation of this type? 4 to the x equals 7. How do you solve that? I cannot write this as a power of 5 or that as a power of 7. So the question really was, the next question of the chapter was, how do we solve such equations? Well, in order to do that, I have to undo this operation. For example, to solve x cubed equals 11, the way I solve it is I have to undo the cubing. X is equal to the cube root of 11. And cube rooting and cubing are inverse functions. They're inverse operations. What I need to do is figure out what the inverse operation is to 5 to the. What's the reverse of that operation? 5 to the. Which brings us to the next major part of the chapter, which was logarithms. The definition of a logarithm is the following. If you have b to a power equaling n, then log base b of n would equal that exponent. anytime you see a logarithm basically equals some exponent. And you just have to figure out what that exponent is. But logarithms are a way to undo and isolate exponents. So this problem, I now know what x is. It equals log base 5 of 7. I'm not sure how to calculate that yet, but I know that that's what symbolically what the answer is. You might remember that when we did logarithms for the first day, mostly we tried to get you used to taking an exponential statement and rewriting it as a log statement, or taking a log statement and rewriting it as an exponential statement. Some teachers call those things log loops. For example, everybody knows that 2 cubed equals 8. So therefore, log base 2 of 8 equals the exponent 3. And just going back and forth between those two gives you some comfort level with the concept of logarithms. All right. So, what is the log base 5 of 25? Again, this equals some exponent. And what exponent does it equal? It equals the exponent 2. Why do I know that's true? Because 5 squared gives you 25. What's the log base 8 of 4? Well, again, it's going to be some exponent. 8 to what power gives you 4? Well, this one may not come to you right away on the top of your head, but again, I can solve this one because I know they have common bases. This is 2 cubed, furthermore to the x. This is 2 squared. So 2 to the 3x equals 2 squared. Again, that means that these two exponents have to be the same. 3x has to be 2, x equals 2/3. That one was probably difficult to do in your head, but if you more comfort level you have with logarithms, you can do things like, what's the log base 16 of 4? And so you're asking 16 to what power gives me 4? Well, the square root of 16 is 4, so if I raise it to the 1/2 power, fractional powers are the same as roots. So now it comes back to the question, well, how do you solve the equation 5 to the x equals 7? I know that symbolically the solution is log base 5 of 7, but how do I actually calculate that? What value does that have? How do I compute that? I can't do it in my head. Well, in order to understand how we do that, you're going to need to know more about logarithms, which means I need to know how logarithms work, how they act. There are rules. For each of the rules of exponents, the familiar ones that you know, there's a corresponding rule of logarithms. For example, this corresponds to that first rule of exponents. It says the log of a product can be rewritten as a log of the first object plus the log of the second object. The second rule says the log of a division can be rewritten. Here's the third rule and the fourth rule. Again, I'm not going to prove all these rules. I just want to remind you that we developed them and that they are useful in order to solve problems. In addition to this fact, there is a corresponding fact for logarithms that says basically if the log base b of m equals the log base b of n, that can be true only if m equals n. So if this is true, then we know that m has to equal n. From there, we understood how logarithms worked. We then started to graph logarithm functions. So from the rules, we went to graphs and then equations. With logarithms, we went from the rules to the graphs and then eventually to log equations. So what about the equation log base 2 of x? How do we graph that? Well, I now know how logarithms can be computed, so I can figure out what's the log base 2 of 1, what's the log base 2 of 2, what's the log base 2 of a number like 8, and I can just plot points. What's the log base 2 of 1/2, or what's the log base 2 of 1/4? And if I plot these points, the log base 2 of 1, if I plug in 1 as my input, actually gives me 0 out. Why is that true? Because 2 to the 0 gives me 1. Log base 2 of 2 is the exponent 1. So if I plug 2 in, I get 1. If I plug 8 in, I get 3. If I plug in the number 1/2, I get -1. Why is this equal to -1? Because 2 to the -1 power is 1 over 2 to the first power. That's the 1/2 I was aiming for. And if I plot these points, you get a graph that looks like this, which is the shape of a basic log graph. Well, remember that the exponential functions for b values that were greater than 1 looked like that. It's no surprise, therefore, that this function is similar to that, and in fact is symmetrical around the line y equals x, because this function is the inverse of the other one. What do I mean by that? Remember that we talked about how to find an inverse function. If this original function was called f of x, I could find the inverse function by switching the roles of x and y. So if I rewrite it as x equals log base 2 of y, that's now the inverse of the original function. If I now isolate the y, I get 2 to this exponent, gives you that result. This would be the inverse function, which is our familiar exponential function. Logarithms and exponential functions are inverses of each other. I could plug in the number 3 here. 2 cubed would give me 8. Or I could plug in 8 into the inverse of that, and I would get the number 3 out. Since I know the behavior of most log graphs, I now know the behavior of most exponential graphs. I now know the behavior of most log graphs. They all go through this point, the anchor point, which is 1, 0. They rise slowly over time. But what's the domain? What's the domain of a log function? Apparently, it looks like the domain is x is greater than 0. What's the range? Well, it looks like I go down forever and up forever. The range is all values. These two things are the reverse of what we had with an exponential function. An exponential function, again I'll draw it here, had the domain of all numbers and had a range that you had positive outputs only. That's your basic exponential graph. Your basic log graph has a restricted domain. Why can I not take log base 2 of a negative input, like -8? Why is that calculation doesn't give us a valid result? Because you're asking basically 2 to what power gives you -8. And even if I raise 2 to a negative power, like -3, that doesn't give you -8. It gives you 1 over 2 cubed, which is 1/8. You can never get out a negative result. I'm taking a positive number and raising it to a certain number of powers, positive times a positive times a positive is never going to give us -8. So there's the graph of a basic log function and its domain and range. I think I'll put that over here. Here's the picture of a log graph. Again, it has an anchor point. All log graphs go through there. This is log base b of x, where it could be any base that you want, base 2, base 10. It looks like that. Quick review of log graphs. We will test your knowledge of log rules, and one way to do that is ask you to do some manipulations. For example, we could give you the following. We could give you log base 6 of 4 plus 2 log base 6 of 3 and ask you to compute that without using a calculator. Well, none of these come out nicely in my head. I cannot seem to figure out what they are. But I do know, if I use these rules, that 2 times the log of 3 can be rewritten as a log of 3 squared. I'm just using this rule, number 3, a way of rewriting an expression. Of course, that's just 9. Log base 6 of 9. Still don't know what that is, but I do at least have gotten it to this far. Well, now I recognize I can actually use statement number 1. That says the log of this plus the log of that can be rewritten as the log of the product. And the log of the product, well, 4 times 9 is 36. And now, once I get all the way down to here, I realize I can do this in my head. This is just an exponent. 6 to what power gives me 36? The answer is clearly 2. So one way to test your knowledge of logarithms is to give you some manipulations like that and see if you can walk your way through them. But eventually you're going to have to use a calculator. And our calculator does have the ability to compute logs, but it does not have log base 3 and log base 7 and log base 8. It has basically only 2 logs, one of which we studied this year, and that's a log base 10. The log base 10 of a number is often just written as log of that number. If you see a log statement with no base written, then that's assumed to be base 10. And that's called the common log, because it's one of the most common ones used. So I can actually do that. I can actually find what is the log base 10 of 392. My calculator has the ability to do that computation. Remember that the log key is right here. It says log. And so if I want to, I can simply go, what is the log of 392? And it gives me the answer. How can I check that answer? Remember, this calculation is going to be 10 to this power should give us what result? Well, it should give us back to this original number, a log loop again. So if I take 10 and raise it to that answer, I should get, of course, 392. No surprise. But how does that help me find the answer to this problem? 5 to what value gives me 7? I do know that that is, by definition, log base 5 of 7, but I don't know how to do that computation on my calculator because I only have base 10 ability on my calculator. Well, there actually is a way to convert back and forth, and just remind you of that. I'll put it right here as number 6, and that is the log base b of a number can actually be converted to base 10 as the base 10 log of that number over the base 10 log of that old original base. And that fact can be proved by a lot of these. But again, I'm not proving these facts or reteaching them. I'm just reminding you of that very key fact. And so when you have this calculation, I can rewrite it like this. I now know that that's going to be log of 7 over the log of 5. The log of the original number divided by the log of the original base. So let's see what that is. That's the log of 7 divided by the log of 5, and I get this number. How can I check that number? Again, that's the solution to that problem. 5 to that number should give you 7. So if I take 5 raised to that strange exponent, I should get, sure enough, 7. So that's how I know it's right. Another way we can test your log rules is we could just give you some expressions and ask that you rewrite them. So for example, we could give you the problem 5 times log base b of n plus log base b of w, and ask that you write that as a single logarithm. Well, we just have to use our rules. Now here's where remembering the order of operations is important. Please don't combine these two first, because you'll be doing addition before you dealt with that multiplication. So deal with multiplication first. This, of course, can be rewritten as log base b of n to the 5th. I was, again, using this rule, one of the ones that students sometimes struggle with a little bit. Then I realize I have a log plus a log. I can combine to a single log by using the first rule, which shows how I can write those things as one single log. That would be this object times that object, and here's your final answer. Simply just asking you to show off that you know the rules by either combining things to a single log, or conversely, I could ask that you take a single log and expand it out. Again, the log of a division could be rewritten as the log of this object minus the log of the other object. And then once I get to there, I realize that I could rewrite this problem as, I can bring the 4 out front as 4 times the log of w. And there is that problem sort of written out as a combination of individual logs. So you're basically showing off that you can go one way or the other. Often what we do, we give you a problem of this following type. Suppose you have log base b of the number 2, and since I didn't tell you what the base is, I really don't know what the answer is, so I'll just call it w. And I tell you that you have the log base b of the number 5, and let's suppose that equals t. If I give you all that information, you should be able to find the log base b of the number 8/5. And it's going to be in terms of w's and t's. So what you want to do is you want to deconstruct this and try to figure out all the different pieces and go from a single log, like I did here, and try to write it into all of its individual log pieces. For example, using the first property of logarithms, this one number 2 over here, I can have the log of 8 minus the log of 5. Now, I was told the log of 5 is the letter t, so I can just simply replace that with the letter t. Not the log of t, just t. This, unfortunately, I don't see what that is yet, but then I realized 8 can be written as 2 cubed. And 2 cubed, the log of 2 cubed, I can rewrite that as 3 times the log of 2, using a property of logarithms. And then this, of course, I do recognize as the letter W. So the answer is 3W minus T. A lot of students find those type of problems a little difficult, but basically all you're doing is showing off that you know the laws of logarithms and you are systematically substituting letters for expressions. That's log simplification or log rules, which then leads us to solving log equations. Here's a log equation. That we could ask you to solve. And we first try to use our rules of logarithms to condense it to a simpler problem. Before I do that one, here's a much easier log problem. What is the log base 3 of x plus 2 equaling 3? Well, if I remember my definition of logarithms, this will actually can be written as 3 cubed equals x plus 2. 3 to that power gives you that result. 3 cubed is 27. So x itself, if I subtract 2, is 25. It's actually fairly easy to solve a log equation if you have a base and an exponent and then you have your result here. You just return it into an exponential statement. In order to do that, however, I need to combine this to a single log. So I'm going to rewrite this as log base 2 of x times x minus 7 equals 3, which then can be written as log base 2 of x squared minus 7x equals 3. And now I have that very similar to what I had over here when I had the log base 3 of x plus 2 equal 3. When we had this problem and we had 3 cubed equals x plus 2, and we very easily solved for x. Once you combine it to a single logarithm, you can then turn the equation into an exponential form. 2 cubed equals x squared minus 7x, which is 2 cubed is 8. And so you get x squared minus 7x minus 8 equals 0, which is a quadratic equation. We can then factor this quadratic equation. X minus 8 and x plus 1, I believe, are the factors. You get negative 8 at the back, you get minus 8 plus plus 1, you get minus 7 in the middle, which leads us to either x has to be 8 or x has to be negative 1. And you're all excited that you solved the original problem, but you haven't, because we remember what is the domain of a log function. The domain of a log function is that the x's have to be greater than 0. You cannot take the log of a negative number. So if I plug in 8, that is going to be positive, that's going to be positive, so that's a true statement. But when you plug in the number negative 1, you're taking the log of the number negative 1, which you cannot do. If any of these numbers make these log inputs negative, they have to be tossed out as extraneous or false answers. So that's the last step you must check with a log equation, is making sure that you are in the domain, in other words, that the log equals, is being taken of a positive number. All right. So we went from exponents to exponential graphs to exponential equations. The only exponential equations I could solve without understanding logarithms were exponential equations like this, which basically can be thought of as 2 to a power and 2 to some other power, common base problems. When we tried to solve a problem like 4 to the x equals 7, I couldn't do it that approach. I had to come up with a definition of logarithms. once we define logarithms, we understand their rules, we understand their graphs, and we can solve log equations. I now want to come back to, though, these type of problems. And in fact, I want to come all the way back to exponential graphs. So we certainly remember what the graph of 2 to the x looks like. So my question to you is, what does this graph look like? 3 times 2 to the x over 4. And we have to remember some of the transformations that we learned earlier in the year. First of all, what does this do? Well, I'm multiplying the original rule being 2 to the x, the parent function, I'm multiplying that by 3. But I'm multiplying it outside of the rule, which will take the original function and stretch it by 3. So if that's 2 to the x, if I now multiply that by the coefficient of 3, that will stretch it vertically, meaning that this intercept is now at 3. It used to be down here at 1. So what does this do to the graph? Well, you might remember I'm multiplying or dividing x. I'm going to change the horizontal scale. And the horizontal scale works differently than you think it should. That means when I divide by 4, rather than make it tinier, you're actually making it longer. When all is said and done, this particular graph does the following. The original parent function was 2 to the x. It passed through the point 0, 1, and then every time you move over 1, you're going to have another power of 2. So this will be 2, and then when you move over another 1, you're going to double that again, so now you're at 4. Basically, you're going to be doubling every time you move over 1. Well, I want to do this graph instead. I want to do the graph of 3 times 2 to the x over 4, and I would like to know, what does this do? Well, we now know that makes the intercept 3. So what does this do? It stretches out horizontally so that it will indeed double, but it doesn't double at 1, it doubles at 4. So it takes it, when x is 4, I'll have 1 doubling. And then, of course, 8, when x is 8, I'll have 2 doublings. And so it stretches it out horizontally. That's great, but where does that all lead us? Well, you might remember that this leads us now to exponential growth and decay word problems. So let me give you a quick reminder about those. Suppose you buy a house for $320,000. Suppose the value of that house increases, and we'll make it increase by 20% every 6 years. You live in this house for a couple years, and eventually you decide to move. So the question is, how much is the house worth 14 years later? These type of problems are called exponential growth and decay problems. It's how populations grow, value grows, how things may shrink over time and decay, and they're quite practical. The general gist of them is that the amount you have at time t is equal to the original amount, your growth rate, t over k. The three numbers right here, here, and here are the parameters of the problem. Those are constants that don't change. The two variables of the problem are time, how many years it's been, and how much the value of the house, or how many people you have, or whatever the thing is growing or shrinking. Those are the two variables. So this particular number is the initial amount. G is your growth rate. I'll just explain that in a second. And K is probably one of the trickier things to keep track of, and that is the length of one growth period. How long it takes to do one of these growings. This is your initial amount. I've described how the house grows, but what does that mean in terms of the growth multiplier? Well, if you have a certain amount and then you increase it by 20% more of that amount, if you factor out the W, it means that you're going to have a 1 plus 0.2. This is your multiplier. Likewise, if you had a certain amount and you lose 30% of that amount, if you factor out that common W, you realize that your growth multiplier is 0.7. So to shrink by 30%, you would multiply by 0.7. To make it increase by 20%, you would multiply by what you had, the original one object, and then increase it by 20% more. There's your multiplier. In any event, your growth multiplier is 1.20. This number is how long it takes to do one of those growths. This is your K value. And so when they describe a exponential growth and decay word scenario, they supply you with those numbers. So I know that the formula is the value of this house at any time is equal to 320,000, 1.20 T divided by 6. And that would describe the behavior of the value of this house. They usually then follow that up after that sentence, and they supply you with these numbers. Then they ask a question. And in that question, they're going to either give you a time and ask for the value, or they're giving you a value and they're going to ask you for the time. In this case, they told us that I want to know what would be the value of the house at that particular time. That's just simply a calculation I need to do. Your calculators can actually do that calculation in the correct order of operations, but you have to remember that this fraction needs to be put in parentheses, because you need to take 1.2, don't raise it to the 14th, and then divide all that by 6. You want the 14 over 6 in the exponent. So here's that calculation. 320,000 times 1.2 raised to the, and here's where I need parentheses, 14 divided by 6. So all of that's being raised, and there's your answer. Does that seem reasonable? Well, it's increasing by, a little bit every 6 years, so 20% hikes would be 12 years. So that looks reasonable to me. That's the house value then. Let's try another one of those. What if I asked you the following? You're going to invest some money at 5% interest per year. How long will it take you to double your investment? In this problem, they didn't tell you the initial amount. They didn't tell you how much money you invested. So I'm just going to leave that as A0. I don't know what that is yet. Now, if you're going to increase it by 5% interest, you're going to basically take what you have and give you 5% more on top of that. Your growth rate is 1.05. Don't do 1.5. That would be 50% interest. But 0.05, 5%, there's your growth rate. That's per year. So it takes only 1 year before you get that growth. Here's your basic equation. Now, they ask you a question. how long will it take you to double your investment? They basically tell you that the amount you're going to have is going to be twice what you started with. Sometimes it ends up that they don't supply you with the initial amount because that doesn't really become important. That's going to actually drop out. If I divide both sides by a 0, that drops out. By the way, you could have also made up your own number. You could have said, let's start with $100, and that would then be $200, and then when you divide both sides by 100, you get to this equation anyway. You recognize in order to solve that equation, I have to isolate the t. The t would be equal to, well, I can use logarithms. Log base of 1.05 of the number 2 actually equals t. This, of course, I can compute with my calculator because I can rewrite this as the common log of 2 over the common log of 1.05, and that's a pretty easy thing. But I certainly need a calculator to do that calculation. I can't do that one in my head. So here is log of 2 divided by the common log of 1.05 gives you that number. About 14 years, 14.2 years for you to double your investment. Again, that looks about reasonable to me. By the way, if you're going to reach for your calculator to solve these problems, you could use other features on your calculator to solve this equation. In particular, you could use your solver key. To use your solver key to solve that, that would be under the Math, and for many of you, Math 0 menu. The equation solver, you just simply type in the equation you want to solve. Now, they have it set equal to 0, so I can go 1.05 raised to the x minus 2 would have to equal 0, and then you go down arrow to your guess. Now, I have no idea what to guess. Here's the good news. There's only one answer to these. And so basically you can guess any number. I guess 5 years. Well, no, the actual answer is 14.2. I could guess actually 58 years. No, the actual answer is 14.2. So the nicest thing of using your solver key to solve log equations is that basically the guess is less important because there is only one answer. Regardless of your guess, you'll get dragged to the right solution. Okay, there's actually two other types of problems I'd like to sort of review you on. And one is called a half-life, which can be solved by using this basic approach. So, for example, the half-life of iodine-131 is 8 days. This is a radioactive substance that's used to treat thyroid cancer, and basically it transmutes and changes so that you have half as much of it after 8 days that you started with. Suppose you inject somebody with 30 milligrams of iodine-131, and the question I want to ask you is, how much is left in your system, say, 30 days later? Now, the thing with half-life problems is that they're actually telling you two bits of information. They're telling you the growth rate, and they're telling you how long it takes to do one growing cycle. And so basically, here's your initial amount, and so here's the problem. The amount you'll have is 30 milligrams. 0.5 is your growth rate. That's always true for half-lives. And it takes 8 days to do one of those growing cycles. There's the relationship between time and the amount you have left in your bloodstream. Now, they ask a very simple question. They say, well, how much do you have after 30 days? So you simply now have a calculation to do. You don't need to use logarithms to do this because you're not trying to solve for an unknown exponent. It's simply a calculation that you just type in, remembering to put this in parentheses. The other type of problem I want to quickly review is compound interest. And compound interest can be shoehorned into this formula, but many people do it the following way. They say the amount of money you have with compound interest is your initial principal, which is your initial amount, and then it's 1 plus your interest rate divided into n installments, n times t, where n equals the number of compoundings per year, r is your interest rate, not your growth rate. So an example of this would be, suppose you invest $200, 8% interest rate, but that's going to be compounded 4 times a year, what they call quarterly. That's 4 times a year. And the question I'll ask is, how much money will this investment be worth in 17 years? The key thing to remember is you take your interest rate, the 8%, and you divide that by 4. You do not take 1.08, because then you'd be taking your principal and cutting that into quarters, which you don't want to do. 8% interest in 4 installments is 2% at a time. So there's your growth rate. Is actually 1.02, because I'm going to give you 4 installments, each of 2%. And your growth period is 1 quarter, but rather than divide by fractions, you realize I want to do that 4 times a year, 17 years. So that's how many times you'll be doing that. And then, of course, you have your initial amount. And there's the calculation you need to do a compound interest problem. So, exponents, exponential functions, exponential equations. Logarithms definition, logarithm rules, logarithm graphs, logarithm equations, leading us to word problems using either the general boilerplate exponential growth and decay situation or the more specialized formula for compound interest. That's a quick review. We're going to give you a worksheet to practice these tomorrow. Thanks.